Okay, so ladies and gentlemen, we're going to be discussing today the third major type of modeling that we're going to be covering out of the dynamic modeling toolbox as part of this course. Previous to being system dynamics modeling, focusing on accumulation processes, feedbacks. Secondly, agent-based modeling, with a particular focus on characterizing populations, each composed of individuals, where those individuals interact with one another directly and through an environment, which allows for influences from the broader model to impact an individual, and those individuals to affect each other's behavior. Today we're going to be talking about the third major type of modeling, which is known as discrete event simulation. Okay? Discrete event simulation. The name is somewhat of a historic factor in the sense that it's not totally diagnostic of this class. It's not really a designation which is unique. Agent-based modeling, as we've been experiencing it, has also used discrete events. They're events that fire at points in continuous time associated with the agent. For example, when an agent transitions from one state to another, or when a message is received by that agent, when an event object in any logic fires. All of those are what we would call discrete events. They're events which occur at a particular point in time and some action is undertaken. However, for historic reasons, there's a whole area of simulation. Maybe someone could get that door. Thanks, Levy. Appreciate it. I'm sure the people out there appreciate it too. There's a whole sub-area of simulation called discrete event simulation, which focuses on phenomena which have defined workflows, where progress along those workflows is gated by, is limited by availability of resources, and where entities, which you could think of as agents at a certain level, flow through those processes. Okay? We're going to take a look at this, and we're going to, in fact, build up a model today together, which exhibits this. Okay? One of these models we had previously seen, and this was a model of a trauma center. Some of you folks may remember this. Within this model, people came in, they circulated within this environment, they waited for care, they were partitioned out for rooms, etc. And discrete event modeling involves a set of building blocks and has a set of features associated with it, which are shown here. A discrete event model makes use of defined workflows or flowcharts, such as that shown here. This is a visual depiction of a sequence of activities, not purely linear, that take place over time. So we have, for example, an individual come in and it's decided whether or not they need a CAT scan, this computer-aided tomography CAT scan. And if so, they have to drink some trace medication and undergo CAT scanning. If not, it determines if ultrasound is needed or if a VQ scan is needed. There are these successive processes that a given patient will undergo. And a given patient here somewhat passively flows through these workflows. If we were to think about, well, there's many contexts in which these defined processes take place. Can anyone give me an idea of other processes which can be diagrammed out in this kind of workflow way? What are some other processes that you might imagine taking place in industry or which you might have experienced yourself, which might be amenable to description in this sort of flow chart sort of way?
Any production line.
Yeah, production line. Yeah, how the cars we drive in are manufactured, or the buses, right? The systematic assembly of these vehicles out of parts. might be represented in this form, and there might be branches associated with, for example, quality assurance processes, right? So they check to make sure that the engine performs according to spec in the vehicle, and if it doesn't, it needs to be sent back for examination or what have you. How about another process that could be diagrammed like this?
Bank teller behind the scenes work.
Sorry?
Bank teller.
Okay, bank tellers, yeah. So service processes of all sorts, in fact. Where you might have a bank, you might have an insurance agency, and don't get caught up in the notion that, flowing through here has to mean that you're physically surrounded by a process. And maybe that you are. It's a car is being assembled along this line, or a patient's presenting for a healthcare facility and is getting treated along the way. They're physically present, but there may be other processes where you apply for, you apply to become a certified engineer, and you go through a set of processes associated with that. Or you put in an insurance application, and it gets reviewed in various steps. You apply for citizenship, and it has to go through a series of processes. These defined processes could represent paperwork involving an individual, and your presence at one point or another may just mean that your paperwork is at that stage of the process, for example. So these sort of defined workflows are seen in many contexts. And one of their common features is that the things that flow through, whether it's paperwork or people, they wait. In order to progress, typically some resource is needed. Maybe you have to be allocated a room to be seen by a doctor, or maybe your insurance application has to be seen by an adjuster in order to be processed. Your claim for an accident has to be reviewed by someone who can assess it. So here we have processes defined. There are flowcharts depicting those processes, but there's limited resources available. And those limited resources mean that there's waiting that goes on. You have to wait for the resource to become available, whether it's a doctor or a procedure room or an insurance adjuster or what have you. And as we'll see, there's also some features involving physical movement. So basically what happens is these things called entities flow through this system, okay? And they're processed by these stages. Note that I'm talking about entities here as individuals, but their role is more passive than for agent-based modeling. Agent-based modeling, they're interacting with each other, they're infecting each other, they're spreading rumors to each other, or what have you. Here, they're competing with each other. Here, they are interacting in a very specific way. They're keeping each other waiting. The fact that you're in that procedure room right now means I can't be. The fact that you're undergoing the x-ray means I have to wait in the hallway. And these resources are required that may be taken up by you or required for my processing and vice versa. Okay? So the entity interaction is predominantly through these resources. And there's physical homes that are often associated with the resources visually. Okay. So we're going to take a look at how to define these models and getting some insight into what they can be used to study by building up a little model, as I am wont. So I'd like to switch over here to AnyLogic. So I'm going to call up my AnyLogic, and I'd invite you, who haven't done so already, to do the same. Okay? Here we go. And I am going to just call this up. And meanwhile, I'd like to be able to go and suspend my virtual machine here. Okay, great. Okay, and let's close that so that we don't have it competing for resources. Okay, just continuing on this kind of line of discussion. We are going to we're going to build up a representation of a process. We're going to define a workflow associated with it, and we are going to define stages of work in which individuals will flow through. And we're going to see how sort of the availability of resources will govern the rate of people flowing through this process. The degree to which they can flow through smoothly, the degree to which they will be waiting while waiting to be served. We'll also see how we can create resource pools that will basically govern sets of interchangeable resources that will allow someone to proceed from a given stage. Okay? A big goal of this sort of modeling is to assess waiting times, the times people spend in the process, and the throughput of the process. What do I mean by throughput? Has anyone encountered that in a networking course or a course on 350 on web programming? What am I talking about throughput?
How many units per unit time?
Yeah, it's a rate. It's how many things I can process per unit time. For a web server, what might we talk about when we talk about throughput? What might we be dealing with? Yeah, how many content requests you serve up in a given hour. Or maybe you're dealing with a job scheduling system where there's requests made to run some process on it, and it's how many of those you can handle per second. If you're dealing with a database system, it might be the number of queries you can handle or the number of transactions you can handle in a given second. Okay? So, ladies and gentlemen, I'm going to go here in AnyLogic, and we're going to create a new model. Okay? New model here. Let me just make sure it's recording. And this model is going to be called DES, so Discrete Event Simulation 1. Okay? The time unit will be hours.
Exclamation mark.
Sorry, not exclamation mark. You don't want that. Hours. Okay? DS1 hours. Okay? So the time unit is hours. Again, that's the yardstick by which we measure time. It doesn't mean it moves only in hours. It's just that's what 1 means. It means 1 hour. Okay? So, ladies and gentlemen, we've just created this model. And next, we are going to go add in an agent type called patient. Okay? This is going to be a patient. Next, we're going to go to the palette, and in the palette, we're going to use the very first library available. This library here, which is going to be called the Process Modeling Library. Okay? And we are going to go to main. Actually, probably before we do that, let's go give the patient a visual representation. So I'm going to go to patient, and I'm going to go down here, and I'm going to go to this pictures, and I'm going to drag in well, there's a patient icon. Let's go use the patient icon. There we go. Fine. We just put in patient. There's nothing special about it. I could have made them a circle. Okay? But we're gonna put that in there. I don't think we'll be using it, but it's good to have it there. Okay, great. Okay. So here we have patient, we have main. Let's go back to main. Let's go down main, and let's go to our palette and go up to the very first item here, which is this process modeling library. Okay? And I'd like to drag in source here. Okay? You can type walk-in. Okay? So that would be people sort of walking into this facility. And you'll notice when we have that when we have this selected, that we can go and set a number of features here. This is a building block. This process modeling library provides our vocabulary, our set of building blocks, out of which we'll build these process modeling or discrete event simulation workflows. So here, ladies and gentlemen, we've defined this one. So we've dragged in source here, and we've called it walk-in. And you'll notice that we can actually set it so that people come in here. This is going to represent a source of, in this case, patients coming in. We can set it by how much time it is between when they arrive. We can schedule a table in a database that says over time when they arrive, or a rate schedule. We can also do this inject function, which would actually place them into this process. Right now, we're just going to say rate, and the rate will be 10 per hour. Remember that our default time units for this model should be hour, and I'm just going to go double check that. Yeah, it's hours, okay? So it's 10 per hour from this walk-in. Okay, so that's going to be our source of agents, okay? And we're going to have a sink for agents down the other road, down the other side of this, that's going to absorb these agents. Okay, next, ladies and gentlemen. You'll notice that in the new agent area of the walk-in, you should select patient rather than simple agent, okay? How did I do that? I went to this walk-in, I went to new agent, I selected patient, okay? Now you'll notice that we can indicate where they should come in visually, but we're not going to tap that right now, okay? We're not going that way yet, okay? And you'll notice that down at the bottom of this, and it's in one of these advanced areas, I believe. Yeah, the agent type coming through this is patient. So these are individual patients that are going to be circulating through this. Okay. Next, I'm going to drag in a sink. Okay, and this is not going to be a kitchen sink, but a sink for patients. In other words, it's going to represent the place to which patients go to exit the frame of the model. So I just went to the process modeling library and I dragged it in. If you drag it close enough, it'll connect it automatically. If it's too far, it won't. You may just want to drag it like this. I'm going to drag it further, and I'm going to show how you can manually connect it. So I'll call that departures, let's say. And here, what I can do is click from one, and I can drag it and click on the other. And that will actually go connect them. Make sure it's green there, okay? So here we have people coming in and set to go out, okay? So I'd like you to run this model. This model is runnable. You should be able to go run it. And what you will see is people coming in and leaving, okay? These counts indicate the number that have come to that point, okay? And you'll notice if you go and, okay, here we go. If you click on this, it actually will say, okay, the rate is this many per second. This many have left on this. And similarly, we have a count over here for departures. That should be departure, not departure. Okay, here we are, departure. Okay. Okay, so here we have a little model. People come in, people leave. Very simple. We're going to start to elaborate this, okay? First of all, we are going to go to the palette, and we are going to add in a delay. There's a thing called delay here, and we're going to add it in between these two, okay? So instead of having them connected to each other, I'm going to have this wired up to exist there in the middle, okay? And this is going to be called procedure. There we go. And you'll notice that associated with this procedure, and pursuant to its name as a delay, we can set here delay time. And here, this time is drawn from a triangular distribution. So these are distributions that are widely used in operations research, less so in traditional statistics. But it looks something like this. It has a peak value at a certain point, a minimum and a maximum. The minimum is not always at 0. You can set it, in general, it'll go from A to B. And this represents a distribution. It integrates, it sums up. The area within this curve is 1. Under the curve is 1. And it's linear on sort of both these sides coming down. So here, its maximum value is at 1. It has, excuse me, its value is between 0.5, let's make it hours, 0.5 hours and 1.5 hours, okay? And it's the highest likelihood value, the most probable, the value range that's most probable is that right around 1, okay? So 1 hour is the single most likely value, okay? So this is a delay time of between 0.5 and 1.5 hours, with the value around 1 being the most likely value. Okay, so we're going to run this thing, and now we're going to see people come, but there's a problem. So here it says an agent was not able to leave the port. And what's going on is that this procedure can only take one person at a time. Once the second person has come in, there's bad news. They can't be treated. There's a capacity of 1, okay? So let's go back to that procedure here. And you'll notice that it has a capacity of 1. It can only treat one person at a time. What do you think would happen if I set that to 2? Okay. Yeah, it'll stop. It'll actually die a horrible death, just like that. See that? Once you have needing more than 2, game's over. It's a problem. It can't actually deal with that. It doesn't have the requisite capacity. What if I were to set it to 10? Do you think it'll be any better? What would I need to set it at to actually have a chance of it working long term?
Maximum capacity or include a cube for it.
Okay, good. So we're getting there. Alex is, as normal, one step ahead. How many people, ladies and gentlemen, suppose this procedure can take between 0.5 and 1.5 hours. Let's consider 1.5 hours on average. How many people might have come in over the course of 1.5 hours? Okay, so 1.5 times 10 per hour, or 15, right? 15 people might have come in during that time, might be queued up. So let's try 15. Let's try 15. Okay. Okay. So here we're running. Okay. Well, we've served 24 people successfully, but this is still not enough. How could that be? How could it be that we've made it 15, which seems very conservative, and yet it's still not enough? Let's try 20. You think 20 will be enough?
If you're looking at the maximum, you should look at the minimum.
Okay, well. Okay, so here we've served 25 people, but it's still maxing out, ladies and gentlemen. What's the problem? Well, we have all of these spots taken. Remember, each person here who comes in here occupies this resource for 1.5 hours, right? And people come in stochastically. they come in at an average rate of 10 per hour. So you could actually have a burst of people coming in, for example, and you need more than 20. Now we could raise it. If we raise it to something like 100, do you think it would this be enough to sort of allow it to run for a while? Yeah, stochastically it's very unlikely, okay, and then it says, yeah, the PLE is only allowed a certain number. Okay, fine. We won't complain about that too much. So 100 is enough, but there's a lot of stochastics that end up impacting whether or not a given capacity is sufficient. It depends on the arrival times of agents, how many are waiting. And right now we're saying basically if there's not enough spots, it's game over. And here with 100 spots, it's very unlikely that we're ever in a situation that all of them are filled by the time that a new agent arrives. But below that, we're not sure. Let's set it to maximum capacity, and let's run. It's a statistical thing, ladies and gentlemen. It's to sort of whether they'll all be taken. So here we set it to maximum capacity, and you'll notice here that at a given time it indicates how many agents are currently being served. For example, right now it's 10 agents, 12, 11, 17. We could see that it's actually exhibiting some variability, around this, around a certain point. It may go up to as high as 20 at some departures. And you notice we've served about 15,000 agents right now. Okay, so ladies and gentlemen, let's take a look at going in and instrumenting this to find times for people to transit. I noted that this sort of modeling, a big emphasis on is throughput and how long it takes people to remain in the system, their length of stay. So let's go over here to the palette, and we are going to drag in from the palette, a report here. It's going to be time measure end and time measure start. So here's time measure start. We're going to drag that in, and we are going to take this and connect it up. Hey, come on. Hey, oh man. Here we go. We're going to connect this up there. So
go exactly over the line, it will connect both of them.
Okay, good. So just like, hey, come on.
Yeah, that's it.
Okay, I can't see it, but there we go. Cool. Thanks, Alex. Sweet. Okay, so it'll automatically kind of solder them up properly. Okay, here we go. Time measure start, time measure end. And ladies and gentlemen, time measure end is going to measure the time it takes to go from this point to this point. Okay, in order to tell it from where to measure the time, when to measure the time, you have to go here and you have to go to this time measure start blocks and set it to use time measure start. So now it's going to compute some statistics for us on how long it takes to go from here to here. How long is it taking a person who reaches this point to reach to this other point? And obviously right now it's going to be pretty simple, but as we elaborate this model and they start to have to wait for resources like rooms or doctors or nurses, it's going to get more complex. So let's run the model, and we should be able to see this time measure start and time measure end here, recording values. So if you click on time measure end, what you'll see is some statistics. Okay, so the mean time is just short of 1 hour. The minimum is 1.5, and the maximum experience so far is 1.448. This is the standard deviation associated with it. And here it shows a distribution, the number that have fallen within these different ranges. And not surprisingly, the single most likely values are right in this area of 1 hour from start to finish. So this quantifies how many times it's fallen within these ranges. Okay? Great. Okay, so we're moving along here. We've defined this this process. Let's further refine this to go and incorporate a dependency on resources. So let's go to procedure, and let's uncheck maximum capacity. Okay? And we're going to change the capacity back to 1. Okay? For now. Okay. Okay. Okay, now what we're going to do is, in order to handle it, we're going to do what Alex suggested earlier. We're going to go drag this a little bit to give ourselves some space. Drag a bit to the left. And we're going to drag in here, ladies and gentlemen, a representation of a queue. Okay? So this thing called a queue here. Okay, so I've just dragged a queue in. So now, this thing is going to have a capacity of 1. We're imagining there's only one nurse on call, and before they see him, they have to wait in the queue. Oh, I screwed up here. Oh man, I did something really bad. Okay, probably if I did, you did too. Okay, so we actually want these things to go to these ports here, not to those top ones, sorry. There we go. These top ones are for more special things that we'll be using, like prioritization, extra prioritization and bulking, cases where people leave without waiting the full time. If they're waiting too long, they punt and they leave. So we want it hitched up to these guys here, okay? So there's a queue, and we'll leave its capacity as a, we'll make it maximum capacity. So we'll have people wait without limits, okay? Here we are, queue. We dragged it in so it's hitched up here, and then we set it so that it has maximum capacity. We're not going to limit its capacity. Okay? So let's run this thing. Let's run her. Okay? Here's our queue. Only one person can be seen at a time, and here's the queue of people. What do you see about the queue size? Why is it growing?
The delay, the procedure is not having capacity to serve a number.
Good. Let's look at it from a system dynamics standpoint. You can think of the queue as being associated with a stock, a number of people waiting. Why? Under what conditions does the stock go up? Inflow is greater than the outflow. What's the inflow here? 10 per hour. What's the outflow? About 1 per hour. Is that stock going to go up, down, or stay the same? It's going to go up, ladies and gentlemen. It's going to go up, and rising it is. Right? It's rising here. Okay. Not surprisingly. It's rising, and now 5,500 people are waiting in the queue. Okay. Let's stop that grim situation. Okay, so another thing we could have done here, I probably should have emphasized, so we could have looked at this time thing, but the time's going to be a little bit misleading here. What do you think, if this queue is growing, what do you think this time is going to be doing? The time to go from here to here. It's going to be increasing. I mean, people are waiting, more and more people are waiting. They're going to be waiting longer. There's more people ahead of them. And indeed, the mean number of hours waited is just rising here like gangbusters, right? Just rising with gangbusters. So, we can look at it, but it's not terribly meaningful because it's a transient thing. It's just going to be rising. Okay. So, let's deal with some situations for this. First of all, let us go represent the fact that people do not have infinite patience. Okay? So I'd like to go take we're going to go take a connector here, and we're going to go here from this point up to this. Okay, so we're going to have to be careful there. We will go over to departures, okay? Now, we're going to go to departures there. And I think it is going to complain bitterly. Okay, so if we go and we do this, I think it's going to complain because basically there's going to be some people that they never get finished in their timing. Yes. So to a queue, but has no enable exit on timeout enabled. The port out timeout here, okay, is connected, but queue has no option. Okay. So actually, the first thing we have to do, sorry, I was too distracted by that other worry. Let's go to queue. This is going to represent balking. And in order to represent this, we need to go to this area of the queue, advanced, and do enable exit on timeout. And then we say, okay, after what amount of time do they leave? And we'll say, well, they'll leave, between uniform. For a given person, they'll be willing to tolerate between 1.0 and 3.0 hours, not seconds, hours. Okay? So enable exit on timeout, and this is the amount of time for them to time out. Okay? There we go. So between 1 hour and 3 hours, drawn from a uniform distribution. Okay, actually it's a happy camper here. It's a happy camper. I was fearing that it would balk because I don't have it switched up to show the hitched up to show the time for those individuals. Okay, so ladies and gentlemen, of the people served right now, a total of about 270, 280 people have been served. In terms of people who have balked here, about 3,400 have balked. Where are people going mostly?
Leaving.
They're leaving. They're coming in, they're saying, I'm out of here, man. The queue is much smaller. Why is the queue smaller?
Because no one's sticking around.
No one's sticking around. So let's take a look at the mean time here. Well, the mean time is no longer growing without bounds. It seems to be around 3.4 hours for people to head through.
No.
Oh, well, okay. Why do you say it's not fully that? That's true.
Because the people that are actually timed out, they're not actually.
Exactly. The balking time people are not actually being counted here. We're giving a very preferential timing to those here who have gone through the procedure. But those people are very special sort of people. They're the less than 10% that actually waited. So let's take a look at the balking people, all right? Because as Milton said, they also serve who only stand and wait. Okay, so let's go up and, hey, come on, stop doing that. Okay, let's go up and do a time measure end. Let's put it up. Hey, come on. Oh man. Okay, there we go. Time measure end, and this will be called time measure. This will be called bulking. This will become time measure end for bulking. And we are going to again time it from time measure start. So which of those do you think will be larger? Those who undergo the procedure. Why would it be larger for them, do you think? Yeah. So not only are they waiting, they're actually undergoing the procedure as well. And the procedure is going to take some time. So the mean time for those who undergo the procedure is 3.4 hours. The mean time for the others is going to be 1.9 hours. Now, mind you, these include many of the people who are waiting a long time, but they didn't go through the procedure, so they're leaving sooner. Okay. Okay. So we have bulking here, but ladies and gentlemen, we're still missing a key element to this. One of the biggest uses of sort of modeling is to ask how much would resources help lower this time spent in the system? How much would it help lower the time spent waiting? How much would it help increase throughput? In order to do that, we're going to need to explicitly represent resources. Right now, resources have been represented only implicitly by having a capacity here. And basically, if they can't come down here, they remain in the queue. They build up in the queue. Let's make explicit our resource dependency, and we'll be able to vary that resource dependency. So we are going to go to the palette, and we're going to add in what's called a resource pool. And this resource pool will be here called a nurse. It'll be called nurses. Okay. Okay. And we could go add it here. I think I will do so to give us some future flexibility. I'm going to do new agent type, and we'll say nurse, a capital N. Okay. We'll give it a representation of a nurse. Okay. Here we'll give it, sure, we'll drag in a nurse representation. So we've just added nurses, and we're going to go to the nurses area, and we are going to set this to be based on a new resource unit, nurse, in the resource pool. Okay. Now, we've added a pool of these resources, and its capacity right now is 1, but we're going to go to main. We're going to go add, as we have many times before, a parameter called count nurses. Count nurses. Okay? And this is going to be of type integer, and its initial value will be 1. By adding it as a parameter in main, we're going to be able to change it by scenario, by experiment. So nurses here have a capacity given by count nurses. Okay? That's the associated parameter. Okay? Build your model, make sure it's happy, because now we're going to undertake 2 additional steps. Okay. Next. So we've added nurses in, but now we have to make the going to this procedure depend on the availability of nurses, okay? So what I'd like to do is to go and select this model, and I'm going to add some space over here. And the space we're going to add, we're going to use to represent a so-called seizing of a resource, okay? The seizing of a resource is basically going to allocate a resource of the designated type. So I'm dragging that in from the process modeling library, a seize, okay? Here it is, seize. And this is going to be called allocate or assign nurse, okay? It's logically getting allocated a nurse, okay? And if a nurse is not available, guess what will happen? They'll wait in the queue. Good. Okay, ladies and gentlemen. Okay. And for assigned nurse, this is a seize, we are going to set it to use a resource set here, nurses. Okay? Now you'll notice this actually comes with a built-in queue as well. So we actually could substitute for this queue rather than having a separate queue here. we can actually just do so with the assigned nurse queue. It comes with that built-in queue capacity. And maybe for visual simplicity, we will do this here. We'll go assign it. AnyLogic actually maintains what's called a service block, which will do all of these things, which is not bad. So now I've just moved this over. So there's the assigned nurse. This basically will go assign the nurse and it will wait otherwise. And I'm going to set it to use maximum queue capacity. Okay? Yes?
Sees whole set at once or unit one by one?
Sorry?
The cease policy,
Yep.
is it the whole set at once or one by one?
Okay. Where that will be a binding issue is it's a little bit misleading as a label here. So really what this comes into is if you have multiple resources that you're grabbing. Let's suppose you need a doc, a nurse, and a procedure room, and some piece of equipment, like a portable ultrasound machine. Suppose you need them all to undergo the procedure, okay? Then the question is here, does it seize them as a block all at once, or does it seize them catch as catch can as each becomes available, and finally it'll get the final one whenever it's available, keeping the others until that other one becomes available. So this is actually, for this case where we have multiple types of resources available.
So it's not the units of the resource set, like seizing whole.
Correct. It's a whole set of different resources, resource types. Unless they've changed that dramatically. We'll see in just a second. But yes, that's my understanding, unless it's been changed dramatically. Next, we're going to go and we are going to we're going to need to release this nurse. So we've assigned the nurse, and now we're going to release him at this point. So we need to drag in a release block to release that nurse, okay? Here we go, release. And we're going to release all seized resources of any pool, okay? There we go. So we don't have to even tell it particular information. Any resource that's been seized, we will go release it. Okay, so ladies and gentlemen, here we go. Now, let's run this thing. So first of all, build, make sure it's a happy camper. Does anyone want me to go over something I've just done? No? Okay, so let's run this. Okay, now you'll notice that there's this queue, and actually we didn't configure the bulking, did we? We didn't yet configure the bulking, so no one's bulking right now. And you'll notice it's building up here, the number of people waiting. Take a look at this nurse. This nurse here is working 99% of the time, having almost no downtime. It's basically utilization 1, complete utilization. Let's try growing the number of nurses, okay? Okay, so here we're going to create a new experiment, and we are going to have 10 nurses, okay? 10 nurses. Count of nurses is 10. What do you think will happen now? Okay, so let's check this out. Okay, we're still getting, ladies and gentlemen, thousands of people backed up. Let's try, I'm doing this for a point. We'll come back to this. 100 nurses. Okay? 100 nurses. We're going to do 100. What do you think will happen now? it's still building up. There's something wrong. Does anyone see something suspicious in this area? How many people are being served at once? One person. Why is that? Does anyone remember back? That's what we told it, the capacity is 1. Now, its capacity should be governed by availability of nurses. We don't have to limit it to 1 because there's only 1 nurse available. We'll set it to be maximum capacity. Now let's try 10 nurses. Okay, here we go with 10 nurses. Okay. Okay, now we're cooking with gas. Look at that. Sometimes there's 10. Sometimes there are fewer than 10. Why is that? Why are there sometimes fewer than 10 here? Yeah, there happen to be less than 10 patients waiting right now. Right now we have about 10. Sometimes it goes down to 9 or 8. It sort of flickers. What's the nurse capacity here? Yeah, 96%, ladies and gentlemen. 97%, right around there. Let's go to our 100 nurses now. What do you think their capacity will be? Anyone want to hazard a guess? Here we go. Yeah, it's about 10%, which kind of makes sense, right? There's 10 people per hour. Each appointment takes on average about an hour. 10 nurses should be able to handle most of those, sort of standard levels of patient volume. You've got 100 nurses. If you have 10 people that have arrived in the past hour, you're treating them with 10 nurses. They'll be done in about an hour for the next batch to come in, and so on. So you've got about 10% capacity here. Okay, what is the time that they're waiting? Well, how do you think this will vary? Let's go first with 1 nurse. How do you think the time will vary here, given that we have disabled bulking? What do you think will happen here?
It'll grow.
Yeah, it'll just grow without bound, right? Here, the mean time, 39 hours, 40, 44. It's not really it's not stationary, it's rising over time. It's going to be just constantly rising. Okay, ladies and gentlemen, let's go look at 10 nurses. Here we go. Here we go with 10. Okay. Here we have a pretty stationary distribution, even without balking. It's about 1.5 hours per person. 1.7, 1.8. It's rising slightly. Rising slightly. 2.4, 2.3, 2.4, okay. 2.5, 2.6. Over the long term, it's actually rising a little bit. What's going on here? What's going on? It's not rising monotonically, but it's perhaps well above what you think it might be possible sometimes. Well, remember, if the amount of time it takes for a nurse to treat people is between 0.5 and 1.5 hours, if that's on the higher side, people are going to back up. If more people come in per hour, they'll back up, and they won't be able to be served. So the number of people waiting in line actually can exhibit quite large fluctuations on the very high side, just because you could treat people faster, but you could treat people faster, and then you just have to wait for the next person. But if you treat people slower, people build up and then have to be treated. And it's easy for that to kind of snowball with more and more people building up there. And so you can get quite high departures here from the average time you might think would be needed. How about with 100 nurses? What do you think it is? So you might think 10 nurses is in balance, but you could still see big fluctuations because on the upper side it's unbounded. It can actually go as high as wanted. It becomes increasingly less likely, but it can go very, very high as the number of people waiting in line grows due to stochastic fluctuations. It can never go arbitrarily low because you can never have fewer than 0 people waiting. And if you have spare capacity, it doesn't help you deal with people who aren't yet here. Okay, here we go. So here we have nurses. What do you think the average time will be here? About 1. About 1. Where does that come from?
Essentially no one in the queue.
Essentially no one in the queue. People basically don't wait for the queue. A nurse is available right away to treat them. Big difference, ladies and gentlemen. On average, 10 nurses is enough to process people, but even there, you're getting some pretty big fluctuations where you can get long waiting times. Very long waiting times, 4.4 hours, right? Something like that is what I got. Because on the high side, it can really build up. On the low side, it doesn't help much. So again, 4.5 hours. Okay, so you might think that's enough. Inflow equals outflow. If you were ignoring stochastics here, viewed it from a system dynamic standpoint, inflow, outflow, right? You had an inflow of 10 people per hour. Here's our stock. This is from a system dynamic standpoint. An inflow of 10. Here's our stock. And within the stock, we'll call the stock X. So this is the number of people in the queue, and we'll call it Q, right? And we're going to have here an average time for them to leave of 1 hour. So we'll say this is equal to tau here. We'll have Q over tau here, right? Inflow equals outflow. This Q should remain constant. Q should remain constant. But here we see with the stochastic fluctuations involved, you can get more people coming in a given hour than 10, in which case that queue is going to build up with only 10 nurses with very high likelihood. You have fewer than 10 people coming in. There can be, you can work through the queue some, but it can never be less than 0. So with 10 nurses, you can get very high departures from what you might think here. Let's create another one. Let's go up to 15 nurses. 15 nurses. All right, here we go. 15 nurses. We'll make it 15. What do you think the average waiting time is going to be here? Okay, so check it out. Just about 1. How fast do you think it decreases? Given that it's 4.5 hours almost, 4.4 hours with 10 nurses, it would seem that the system is in balance from a system dynamic standpoint. If you look at it from a deterministic standpoint, it seems it's in balance. But from the stochastics, it's not in balance. If it's off in the upper side, it really can build up. If it's off on the lower side, it doesn't help nearly as much. How quickly does it decrease from 4.4 to this just about 1? Let's try it with 12 nurses. 12 nurses. Okay. Here we go. Try it with 12. What do you think? What do you think is going to be the implication here? Be closer to 1 or closer to 4.5? Quite close to 1. Just a little bit of extra capacity to handle those stochastic fluctuations makes a really big difference. If you want, you could try it with 11. 11 nurses. Stochastics, ladies and gentlemen, can make a big difference. They can make a big difference. It's not merely enough to sort of look at the average case, the sort of typical fluctuation. You can fool yourself in some systems by considering it. Here we have 11 nurses. We have it down to somewhere around 1.3, 1.2. Not nearly the 4.4 that we see with 10. Sharp decreases are possible once you go beyond that. You just have to have a little bit of extra latitude. So if things seem equally balanced in a stochastic system, you could fool yourself because it's the bursts that kill you. Let me analogize that to the web situation, ladies and gentlemen. For those people who don't heavily involve simulation, maybe you're interested in web-based systems. It's the bursts that you need to prepare your systems for on the web. It's the bursty traffic, not the average traffic day to day that you care about. When we build computer systems, particularly concurrent systems, that have to deal with multiple users all interacting at the same time, it's during the burst periods that the crunch happens, that we really have to be careful for it to be correct, that we need transactionality. That's when the systems tend to break down, when they're under stress. So it is here. Okay, even a system you think's in balance, not fully so. You need a bit more capacity to bring it down into comfortable levels. Okay, so here, ladies and gentlemen, we've seen a simple discrete event model. This discrete event model has shown some features associated with it that are very common. The ability to ask what-if questions about resource levels. How does it impact time through the system? How does it impact the waiting times or waiting list size? This ability to represent multiple lines of movement through. This focus on sort of assigning and releasing resources and measuring times as part of it, okay? So some important features there. That's not all of them. Okay, so let's take a look at this. Let's go take a look at some of the outcomes. First of all, we're going to go to this assign nurse branch, and we are going to go set it so that we can allow for bulking. Okay. So assign nurse, and down in this advanced area, we're going to enable exit on timeout. Okay. And once again, we're going to do it between, what was the number that we used before? 1.5 and 3 or 1.0 and 3.0 hours. Okay, here we go. Okay, here we go. Okay, so we're going to have exit on timeout here. Let's make sure that works, to make sure people are timing out properly before we go to on to this next stage. We're going to put in place some further utilization measures. Okay, so here we go. And indeed, there's a lot of people timing out, 400 compared to 50 being served, etc. Okay, great. Okay, so next, I would like to set it so that we go to the following. Okay, so we are going to go and add a graph in from the analysis palette. We're going to add a time plot, and this time plot is going to give us the utilization associated with the nurses. So we're going to allow it to update time automatically. We plot nurse utilization, and the data plotted will be called nurse utilization, and the value would be nurses.utilization. Okay? Great. Okay. Excellent. Okay. Next, I'd like you to run this. So we're going to run it here for the simulation, and we may have to adjust some of those parameters of the graph so it retains more data points. But essentially, we see nurse utilization going up to essentially 1, right? Let's set this thing to run. I should have done this earlier, but let's set it to run to display up to 1,000 latest samples, and it'll be a time window of 1,000 model time units. Okay? 1,000 hours, so about 50 days, a little bit less than 50 days. Okay, great. Excuse me, a little bit, yeah, closer to 40 days. Yeah. Okay, great. So what we should see with a single nurse would be essentially maxed out utilization here. Okay, this is even with bulking, they're going and it's essentially maxing out. Okay, let's now try it with the 10 nurses. There we go. So with 10 nurses, we're not seeing 100% utilization, but we're seeing something very, very high, upwards of 95%. Let's try 12 nurses, or try 11, since we created it earlier. Okay. There we go. Okay, so here we're seeing about 90% or so utilization. And you'll notice that once again it kind of wanders around. It's in a pretty defined band, but it wanders around stochastically as people come in and leave, etc. By contrast, if we go to something like 15 nurses, we'll see some notably lower utilization here. Okay, so there we'll see something like 70% utilization. Okay, so here we have utilization that are measured. Okay, so I think we will right. Okay, so the question is, do we have time for this? Okay, so let's add in the final 10 minutes here. So I'm going to save this, do a save as model DES2, and we are going to put in quick order, put in a count doctors, okay, and next I'd like you to put in from the process modeling library, put in a resource pool, and this will be called doctors. Okay, great. And we're going to make the number of doctors in the doctors pool just depend on count doctors, and count doctors. So the resource pool should depend directly on count doctors. Count doctors here is an integer. Got to set it to an integer, and it should be default value 1. Okay, great. Okay, next. We are going to set here we're going to need to add some space here. We're going to change the title for procedure to be initial workup. So that's just the nurse sort of checking out some of the basics. Following that, and in the nurse's presence, we are going to have the doctor get involved as well. Okay, and what's going to happen here is that we need to have a seize block and a release block, etc., associated with the doctor. Okay. Now, there's something that combines all of them, and it's called a service block. And in the interest of time, I'm going to put that in there. we just dragged a service block in from the process modeling library, and this will be called HPD, the history, physical, and diagnosis. Okay, so this is going to be what the doctor is going to be responsible for particularly. And it can only take place after the initial workup. Okay, here we go. Okay, the HPD is going to depend on a doctor, a single doctor, and it is going to have a maximum queue capacity. Someone could be waiting from the initial workup to this HPD for the doctor, as many people as needed. And for the time waiting here, we're going to need to have a delay time here associated with this, and this is going to be the 0.5, 1.5 hours. We're going to switch the initial workup to be a shorter time here. Okay. So here we go. And actually, I'm sorry, I'm going to change this. Look at my notes here. I'm going to change this to be 15-minute to 30-minute to 45 minutes for the doctor. Okay. And here we are going to, we don't have to worry about sending them or balking. Okay. Here we go. Great. And finally, before the nurse can be released, we are going to have a further nurse-specific workup, and that will be called final steps. And so we're going to drag in a nurse-specific delay block here. Okay, so it's going to be a nurse-specific delay block, which does not need the doctor. Boom. And this is going to be called final steps. Okay, this is only going to require the nurse, and it is going to be of duration 10 minutes. Okay, it's a very defined thing. Okay, so 10 minutes for cleanup. HPD is going to take 0.5, triangle of 0.5, 15 minutes, 30, and 45. Yeah.
Does the service block automatically release the doctor?
Yes, yes, it will seize and release that doctor. Right.
For your final steps, did you want it max capacity?
Good question. For this block here, yes. If there's a choice, yes, there is. Yes, thank you. Yeah. Good. For the initial workup, we're going to go back, and that is going to be changed from being that hours to being from 5, 10 to 15 minutes. Okay, so that's like the patient being weighed, etc. So this is in minutes here. Okay, so initial workup, 5, 10, 15 minutes. HPD, 15, 30, 45. Final steps is going to be 10 minutes. Okay, so let's run this thing. So we have a doctor, we have nurses. The nurses are needed for these two steps. The doctor is only needed for the HPD step. There's only one doctor. There's a bunch of nurses. Okay, so let's run this thing. Okay, here we go. Okay, so here we have a situation. I just ran the default, the simulation. Here we have a situation where what's going on? Can anyone tell me? Characterize the situation. What's happening?
Doctors are waiting on nurses.
Yeah, doctors. This doctor is not busy. She's not busy most of the time. She's waiting for this nurse. And the nurse, he's totally maxed out. 99% capacity, maxed out, utilization, maxed out. The doctor is actually not. Okay, now let's go to the situation where we have 10 nurses. Now the timing is off because we've changed the relative time for things. But Now we have a situation where the doctors, well, who's the bottleneck now? Who's more of the bottleneck? The doctor. The doctor's maxed out at 98% of the time, whereas meanwhile the nurses, well, they've got a bit of slack. Okay, well, I shouldn't say slack. I mean, they're really still pretty maxed out, but not as bad. Let's go to 12 nurses. Okay, here we have a situation where, the doctor has very high utilization. Nurses have pretty high utilization as well. Okay, I'm going to go to 15 nurses. Okay, 15 nurses. Both doctor and nurses have, again, pretty high utilization. It's kind of interesting. Let's go to the 100 nurses. We have a phalanx of nurses. Here we go. And here, the doctors are pretty maxed out, but the nurses are still going up pretty high. Why are the nurses so high? Exactly. So a lot of nurses are waiting on what? On the doctor. The nurses are waiting here. You could see them right here, right? So in other words, they did the initial workup. The patient's waiting here, and guess who's waiting with them? The nurse. The nurse is waiting here for the doc to be busy. So here we have a situation where this is coupling, where yes, the doctor's the bottleneck. So do you think if we increase the number of nurses here, it would really greatly decrease the amount of time taken? No. They'd be just waiting on the doctor more. Do you think if we increase the number of doctors here, it would increase it? It would increase throughput? Well, let's do it. We're going to do it to 10, right? Okay. Now we're starting to see some progress. Here, the nurse utilization goes way down. I switched the number of doctors to 10. How did I do that? I clicked on this thing. The nurse utilization drops precipitously because nurses are waiting on the doctors here. So we have these resource dependencies, but there's undeniable that one of them's the bottleneck. After all, if I increase the number of nurses here, it's not going to help a lot. They're going to be waiting on the bottleneck, who's the doc, okay? So these sort of models can help you identify these bottlenecks too. Bottlenecks between resources. How much if I add to a resource is it really going to help decrease the amount of time taken, okay? That's all we have time for today. This is a glimpse of discrete event modeling. And we are soon going to go on to look at how this can be combined with agent-based modeling to allow for coupling of what's going on in the population, for example, with what's going on in a service facility. This sort of modeling, discrete event modeling, is a great language for describing service facilities. It's not a very good language for describing very flexible processes or processes out there in the population, which aren't structured. Here we have a very structured process, and we can describe it with an economy of mechanism using this vocabulary. Okay? So that's all for today. I did release problem set 4 for this class. That problem set has 2 problems on it, on that assignment. One of them involves a topic that we saw covered during a video, but I will answer questions about next time, and that is calibration. The other problem on there deals with movement and creating flocking behavior in agents. For that, you already have all the pieces to get started on it, okay? So you should be able to get started on the assignment soon, and I would advise doing that. It is close to the end of the term, and I'm glad to answer questions. Next time, I'll be specifically pausing to talk about parameter variation and calibration because we did cover them via video. I want to make sure that your questions are answered, okay? So that you can especially get started on problem set 4. Okay, so that's all for today. I will be holding office hours now. I appreciate your patience while I was away. I'm going to hold office hours over in my office today because I don't know about you, but I'm finding the air quality over here pretty spotty, and sometimes I get diesel fumes and so on. And so I've complained to FMD, and we're trying to work on it to see if we could get a better environment. I'm going to be over at my office, 280.6, and I'm glad to meet with students there. It's just I'm not going to be doing it here like normal. Okay? Thanks.